Hello friends, welcome to this video lectures of experimental stress analysis. So today my name is Avinash Parkhe from Department of Mechanical Engineering, Sweris College of Engineering, Pandharpur. So today we'll discuss about the chapter number 3 of experimental stress analysis. Name of chapter is the photoelastic materials. So in this chapter we are going to study the different properties of the photoelastic materials or the photoelastic sheet. Then we are going to discuss about the casting technique of the photoelastic sheet. Then different materials of the photoelastic sheet. Then we'll discuss about what is meant by the calibration of photoelastic model and how the calibration will be done by using the three methods. So we are going to discuss the three methods of the calibration. That is, first one is the tensile specimen, circular disc, and the beam model. So the basic overview of this particular chapter is that we are going to discuss the various properties, because when the photoelastic material is used for the analysis, it is necessary to satisfy some of the properties by that particular photoelastic material. Then whatever the models we are using, so to prepare that models, initially we have to prepare a one sheet having the different amount of thickness or different types of thickness. And if we have to prepare that particular sheet, so that such types of the sheets are prepared by using the casting technique, and that casting technique also we are going to discuss in this particular chapter. Then we are going to discuss about the different materials. So if we have to carry the, or if we have to perform that particular casting process, which materials are required to perform that particular casting process, that all the types of photoelastic materials we are going to discuss along with their properties. And last, we are going to discuss the calibration of photoelastic model by using this particular three techniques, that is tensile specimen, circular disc, and the beam model. Now we'll start with the first point, that is properties of the photoelastic material. So as we know that the concept of the photoelasticity is applicable only for the transparent material, but instead of it is called as a transparent material, we can call it as a photoelastic material. So whatever the photoelastic sheet or whatever the photoelastic material is inspected by using the polariscopic device, so before that particular inspection, so whatever the sheet has been prepared by using that particular casting process, or whatever sheet we have prepared before that inspection or during the inspection, some of the standard properties are there. That property should satisfy that particular photoelastic or for that particular photoelastic material in order to get the good result. So in this particular chapter we are going to discuss about the total 11 important properties of the photoelastic material. So if you go through the slide, there are total 11 properties are there. So out of that 11 properties, one by one we'll start. So first property is the transparency. So the transparency is one of the important properties of the photoelastic sheet or the photoelastic material, because as we know that the light source is one of the important element of the photoelasticity concept, because when the light is passes through the photoelastic material and that material or that particular model is in loading condition in the polariscopic device, then and then only it is possible to obtain the certain fringes. So when it is possible, when the light is passes through the photoelastic material. So to pass that particular light from one side to the another side, that photoelastic material or that photoelastic sheet should have adequate amount of transparency. That means when the light is inserted from one side, as it is the number of light rays which are present to one side, as it is that light sources should, or that light rays are come to its another side, then we can say that this particular material is having the good transparency. So it is one of the important properties of the photoelastic material. So the transparency of the photoelastic material should be high. Then second one is the linearity. So we know that the linearity, so the concept of the linearity we have studied in the strength of material, that is in the stress strain diagram. So as we know that if you go through the stress strain diagram, there is one rule is there, that is Hooke's law. So what is that Hooke's law? Within elastic limit, stress is directly proportional to the strain. So within elastic limit, stress is directly proportional to the strain. So if you go through the figure for the linearity, so there are two diagrams are there, that is stress versus strain, and another is the sigma 1 minus sigma 2 versus n. So the first figure represents the Hooke's law. So up to the certain point, whatever the stress is induced in any material, so according to that stress, the strain value also get changed, and that stress versus strain, it's a linear, that means they are directly proportional to the each other up to the certain point. So this particular property is applicable for any type of material, that is within elastic limit, stress is directly proportional to strain. But in this particular chapter, that is we are using the photoelastic material, so along with this particular properties, our material should satisfy one more linearity properties, which is represented by the second figure. So what is that particular second figure? So the sigma 1 minus sigma 2 is equal to, so sigma 1 minus sigma 2 is directly proportional to n. That means when the value of n is increases, the sigma 1 minus sigma 2 is also going to increases. That means whatever the force or whatever the load is applied on the photoelastic model, so according to the force, according to the load applied on the photoelastic model, the fringes developed in the model is also increases. As the fringes in the model is increases, at the same time sigma 1 minus sigma 2 is also goes on increasing, because sigma 1 minus sigma 2 is directly proportional to n. Therefore both this parameter, that is sigma 1 minus sigma 2 and n, they are directly proportional to the each other up to the certain limit. Therefore that linearity property should be satisfied by that particular photoelastic material. Then third property is the sensitivity. Now this property is very important in the concept of photoelasticity, because our photoelastic material should be sensitive. That means when the model or that particular photoelastic material is comes in contact with the loading, that load may be tensile, that load may be compressive, load may be bending. So after application of load, immediately the fringes should be developed. If the fringes are developed immediately after the application of load, then we can say that the material is sensitive. But if we are applying the large amount of load on that particular model, but there is no any fringe developed, then we can say that the sensitivity of the photoelastic material is less. But during the analysis, during the inspection of any type of photoelastic material, it should have adequate amount of sensitivity or large amount of sensitivity, due to which after application of load, the fringes should be developed in the photoelastic model. Therefore the third property is also very important as compared to the remaining or first two properties. Then the fourth properties is the modulus of elasticity, which is also called as a Young's modulus. So as we know that, so any type of material, that material may be metal is there, material may be transparent material is there, each and every material is having this particular properties, that is Young's modulus or modulus of elasticity, which is indicated by the capital E. And the modulus of elasticity of photoelastic material should be high. Why it should be high? Because when the force or the load is applied on the photoelastic material, their geometrical shape will get changed. Means what happen, if I will take the example of circular disc. So if the load is applied on the circular disc, so after the application of load, sometimes what happen, there is a possibility to change the geometric shape of that particular circular disc, because if the maximum amount of load is applied on it, that circular disc, it changes their shape. Maybe it will be converted into the circular cross section to the elliptical cross section. That means that model has changed their original shape. So and after a few times there may be possibility, that is the deformation of model, and that model will get break. So to avoid this particular disadvantage, that is after the application of load, the model should not changes their original shape, or there should not be any deformation. So the modulus of elasticity of that particular photoelastic material should be high as high possible. So this is about the modulus of elasticity. Then the fifth property is the figure of merit. So the definition of the figure of merit, so it is defined as the ratio of Young's modulus to the material fringe value. So here this particular figure of merit is represented by this particular formula. Figure of merit is equal to Young's modulus upon F sigma. If we go through this particular formula, that is figure of merit is directly proportional to E, and the figure of merit is inversely proportional to the F sigma value. So according to this particular two parameters, that is figure of merit and Young's modulus, so if I will compare these two particular parameters, the figure of merit of the photoelastic material should be high. Why? Because the figure of merit is directly proportional to the Young's modulus. Because what is our requirement? The Young's modulus or the modulus of elasticity of the photoelastic material should be high as possible, and as this E is directly proportional to the figure of merit, therefore that figure of merit of the photoelastic material should be high. Then the sixth property is the isotropic and the homogeneous. So what is meant by the isotropic? If the photoelastic material should have, or if the photoelastic material, or if any material is having the same properties in all direction, then this material will be considered as a isotropic material. Means there are mainly three directions, that is x, y and the z. So whatever the Young's modulus of any material is there, or whatever the Young's modulus of photoelastic material is there, that Young's modulus value is same in the direction of x, it is also same in the direction of y, and if it is same in the direction of z, then we can say that that photoelastic material is isotropic material. Then what is meant by the homogeneous? That homogeneous means if whatever the material is prepared, that material is prepared by using the number of particles. So if each and every particle is having the same property, then we can say that that material is homogeneous. That means that isotropic and the homogeneous materials are depending upon the each other. So this is about the sixth property, isotropic and the homogeneous. Now seventh property is the time age effect. So this is very important property of the photoelastic material, because when what is our requirement? If the load is applied on the photoelastic model, their physical properties will get changed, and that change in physical properties will be observed in the form of different types of fringes. When fringes are developed, if that model or if that particular photoelastic material is subjected to loading. But what happen sometimes, if that particular photoelastic material or any photoelastic model is kept in atmosphere under no loading condition, that means if I will take one rectangular plate which is made by the photoelastic material, and if I will keep that particular rectangular plate as it is in the open environment without application of load, so after a few days, so what happen, without application of load, then also we can obtain, or then also we can observe certain fringes developed in the model. Why such types of fringes are developed? Because whatever the dust particles, whatever the water particles, environmental dust particles are present in the atmosphere, that all the particles are interacts with the photoelastic model, and then we can observe the certain fringes. But what is our requirement? The fringes should be developed after the application of load. But here the fringes are developed because the model is kept in atmosphere for a longer period of time. So such types of the situation should not be happen. Therefore, what is our requirement? Once the analysis is done, or once the model is inspected in the polariscope, we have to keep that particular model in closed box. Therefore, there should not be direct contact between the environmental dust particles, environmental water particles, and in between the photoelastic model. So whatever the time age effect of the photoelastic model is there, that time age effect is less. Then next property is the machinability. So it is very important properties which is applicable for any type of materials. Because why this property is important? So once we are doing the casting process, so in the casting process you will get a big amount of sheet. But what is our requirement? From that particular sheet we have to prepare the different types of models. That model may be circular disc, model may be tensile specimen, model may be rectangular plate, model may be square plate. So to cut that particular all the models from the big sheet, what is our requirement? We have to perform the different types of machining operations. Maybe the cutting operation is there, drilling operation is there, milling operation is there. So all these operations we have to perform on that particular sheet. So that photoelastic material should have good machinability properties, so we can perform such types of all the machining operations on that particular model or on that particular sheet to prepare the different types of model. There should not be any breakage, there should not be any damages while performing all the machining operations on that particular photoelastic model. Therefore, the every photoelastic material or every photoelastic sheet or the model should have good machinability property. The ninth property is the creep. So the concept of the creep is related to the temperature, because what happen when the photoelastic model is comes in contact with the temperature, there may be possibility of deformation. But in our case, when the model is loaded in the polariscope and the load is applied, so there may be possibility of deformation of model when that model is subjected to the loading condition. Means deformation is taking place after the application of load. But in the concept of creep, the deformation of model is taking place if that same model is comes in contact with the temperature. But there should not be any direct contact between the photoelastic model or the photoelastic material or in temperature. So the creep of the photoelastic material or creep of photoelastic model should be less. Then 10th property is the residual stresses. So what happen once the photoelastic sheet or the photoelastic models are prepared by using the casting process, sometimes due to some faulty casting procedure, the sheet will be obtained in the irregular manner. So once it is obtained in the irregular manner, so some of the stresses or some of the residual stresses are developed in the sheet to its boundary. So what we have to do, we have to cut that particular sheet from all the four sides. So due to that cutting operation, whatever the residual stresses are developed, that residual stresses will get decreases by some quantity. So that particular residual stresses will be less in the photoelastic material. Then last property is the cost of the photoelastic material. So whatever the casting operations we are performing, so for that particular casting operation, whatever the materials are required, nowadays these materials are easily available in the market with the reasonable cost. Therefore, the cost of the photoelastic material should be less, or it is always less. So these are the total 11 properties of the photoelastic material which should be satisfied after the model or after the sheet has been prepared by using the casting process, or before inspection or after the inspection. All these 11 properties should be satisfied by the photoelastic material. Then we'll discuss about the casting technique of the photoelastic sheet. Now such types of the photoelastic sheet, sometimes it is available in the market, but sometimes if it is not available in the market with the reasonable thickness or as per our requirement of thickness, so we have to perform the operation of a casting. So we know about the casting process which we have studied in the your second year. So what is meant by the casting process? So in the casting, one mold is there, one liquid is there. That liquid we have to pour in that particular mold, and once after the 24 hours, if we open that particular mold, you will get that particular solid product. So same operations we have to perform to prepare the photoelastic sheet. So if you go through the figure, that figure represents the molds used to prepare the casting sheet. So if you go through this particular first figure, so this is the mold of the sheet casting in the disassembled position. So this first sheet is called as a sheet number 1, this is the sheet number 2, and in between sheet number 1 and the sheet number 2, one more sheet is provided. That sheet is called as a spacer. Why it is called as a spacer? Because if you go through the construction of this particular spacer, this particular space is available to pour the liquid. So therefore this particular central sheet is called as a spacer, and this particular space is we can vary as per our requirement. That means if we have to prepare the sheet having the thickness 10 mm, then you have to take that particular spacer having this particular space is 10 mm. If we have to prepare the sheet having thickness 5 mm, then we can replace this particular spacer and we will take the another spacer having this particular gap of 5 mm. Therefore this particular element is called as a spacer. So this is the mold for the sheet casting in the disassembled position, and this particular second figure represents the same mold, but it is in assembled position. Once again, if you go through the construction, so this particular portion is called as a sheet number 1, then last portion is the sheet number 2, and the central portion is called as a spacer. That means the spacer is provided in between sheet number 1 and it is provided in between sheet number 2, and this particular hole indicates the screwing arrangement. Once all the sheets are assembled together by using the nut and bolt, we can tight this particular all the sheets to each other. Therefore your mold becomes tight proof and the leak proof. So this is about the preparation of mold before liquid is pouring in it. Now we have to focus on the which materials are used for the sheet casting and what is the exact procedure to prepare that particular liquids. So for the sheet casting, basically the two important materials are used. So first one is a araldite, which is called as a CY 230 or 231, and second one is a hardener, which is called a HY 951. So these both the materials are nowadays easily available in the market with the reasonable cost, and nowadays these two materials are also used for the sheet casting. So what is the ratio of this particular two liquids? So the ratio is 100:10 or 10:1. So always we have to use that particular araldite in the larger quantity, and the hardener is provided as a resin for the curing purpose. So always we have to use the araldite in the maximum quantity and hardener is in less quantity, means we have to take the ratio of 100:10 or 10:1. For example, if I will take the 100 gram araldite, then I have to take the 10 gram hardener, means I have to add this particular 10 gram hardener in the araldite. Now we'll discuss about how the casting liquid is prepared. So once now your mold is ready for pouring the liquids, now we have to focus on the preparation of casting liquid. So initially what we have to do, so we have to take the araldite as per the requirement of the mold. Suppose for this particular mold the 100 gram araldite is required. So what I will do, I will take the araldite in one pot from that particular bottle. So what happen, while taking that particular araldite from bottle to that particular pot, some amount of air bubbles are developed. So what is my requirement? Before pouring that particular liquid in the mold, all the air bubbles should be removed. So what I have to do, I have to heat that particular araldite at some 40 to 50 degrees Celsius. So due to that heating process, whatever the air bubbles are developed in that particular araldite, all the air bubbles are removed. Once the air bubbles are removed, we have to keep that araldite for the atmospheric condition for the curing purpose. Then after that, what I have to do, once the araldite is properly cured, I have to take the 10 gram hardener. Why 10 gram? Because araldite I have taken as a 100 gram, and for that purpose I have to take the 10 gram hardener. Once I will add the 10 gram hardener in that particular araldite, so after that what I have to do, I have to steer that particular mixture of araldite and hardener in only one direction. That means I have to steer that particular liquid maybe in anti-clockwise or in clockwise direction. Why it should not be in clockwise and anti-clockwise simultaneously? Because once I will rotate in particular clockwise direction, less amount of air bubbles are developed, but at the same time if I will rotate the liquid in clockwise as well as in anti-clockwise direction, again some extra air bubbles are developed. So the requirement is that the mixture of araldite and hardener should be steered in only one direction for the 10 to 15 minutes. Once the 10 to 15 minutes are over, then your liquid of araldite and hardener is ready to pour in that particular mold. But before that pouring that particular liquid in the mold, what we have to do, so if you go through the mold once again, so maybe due to during that screwing arrangement, there may be possibility of some gap in between sheet number 1 and spacer. Sometimes there may be possibility of some amount of gap in between sheet number 2 and the spacer. So due to that particular gap, what happen, there may be possibility of leakages. So what we have to do, there is one wax material is there. That wax material we have to apply to this particular corner edges, so your mold becomes tight proof and the leak proof. Once that particular wax is applied, we have to pour that particular araldite and hardener liquid through in that particular mold from this particular top position, and we have to keep that particular mold on the horizontal surface, or we can keep that particular mold on surface plate, because that surface plate is perfectly horizontal. Why we have to keep that mold on surface plate? Because if I will keep that particular mold on any inclined surface, so whatever the sheet is prepared, that sheet is also prepared in the inclined position or in the irregular shape. So to avoid this such types of the situations, we have to keep that particular mold on the surface plate. Therefore sheet should be prepared in properly or in the proper shapes. So we have to keep that particular mold for 24 hours, and once I will open that particular mold, you will get the sheet as per the thickness of the spacer. But sometimes what happen, if the sheet is prepared in the irregular manner, so there may be possibility of residual stresses. So we have to cut that particular sheet from the all the four sides. So due to that cutting operation, by some percent some residual stresses will get removed, and after that from that particular sheet we can cut the different types of models like circular disc, tensile specimen, square, rectangular plates, and this all the models are inspected by using the polariscopic device, and whatever the results are obtained from for that particular models, the same results will be considered as the results of the photoelastic sheet. So this is the actual procedure, or this is the actual process of the sheet casting. So in the sheet casting of the photoelastic sheet, only we have to focus on the two important parameters. That is, first one is the preparation of mold. That means while preparing the mold, which care should be taken, that I have explained. Once the mold is prepared, then we have to focus on the second parameter, that is preparation of casting liquid. That means while preparing the casting liquid, what care should be taken, how the araldite is heated, why the araldite is heated, why it should be steered in only one direction. Like that, all the cares we have to take while preparing that particular liquid. And once the mold and liquids are prepared, we have to pour that particular liquid in the mold, and the requirement is that we have to keep that particular mold on the perfectly horizontal surfaces, or we can keep it on the surface plate to avoid the further disadvantages, that is, it should not be formed in the irregular shape. So if we take care about that, then your sheet has been properly prepared. So this is about the casting technique of the photoelastic sheet. Now we'll discuss about the different photoelastic material. So now whatever the casting technique we have discussed, in that casting technique we have discussed about the mixture of araldite and the hardener. But in addition to that, some another materials are also there which are used for the sheet casting. So total 6 materials are there which are used for the sheet casting. So one by one we'll discuss about all the materials, but each and every material is having some of the important properties, and that properties are available in the form of some advantages are there, some disadvantages are there. So one by one we'll discuss about all the materials. So the first material is the Columbia resin. So it is also one of the materials. So all the materials are available in the form of liquid form. So the Columbia resin is also available in the form of liquid form. So that Columbia resin is also used for preparation of the photoelastic material or the preparation of the photoelastic sheet. But this material is having some of the property. That is, first property is the Columbia resin is highly brittle. Then second property is the surface finish is extremely good. So whatever the sheet has been prepared by using this particular Columbia resin, it is having high surface finish. But one disadvantage is there, it does not have any linearity properties. That means whatever the linearity property we have discussed, that is sigma 1 minus sigma 2 is directly proportional to n, that property is not satisfying by that particular Columbia resin. And the last property is the time age effect is present. That means whatever the sheet is prepared by using the Columbia resin, if that particular sheet will keep in atmosphere, directly that water particles are comes in contact with that Columbia resin, and immediately the fringes are developed. So these are the some properties of the Columbia resin. Then the second material is the Homolite 100. It is also one of the material which is used for the sheet casting. It is also having some of the properties. That is, first property is the it is tough, and second property is that low creep and the time age effect. So whatever the creep property is there, or the creep concept is there, that creep is very less in the homolyte material, but some time age effect is present. That means if that homolyte is again, if it comes in contact with the temperature, or if it is comes in contact with the atmospheric condition, again certain fringes are developed. Then the next property is the polycarbonate. What is mean by the polycarbonate? Again, it is the another material which is available in the form of liquid form. Again, it is having the some of the properties, that is, it is very tough, low creep, time age effect. That means each and every material is having some of the properties in the form of advantages and the disadvantages. Then again, the next material is there, that is urethane rubber. That urethane rubber is also having some of the properties. That is, first property is the low Young's modulus. That means whatever the modulus of photoelasticity is there, that E factor is very less to that particular urethane rubber. Then next property is that used for the demonstration purpose. So whatever the photoelastic sheets are prepared by using that particular urethane rubber, that sheets are only used for the demonstration purpose. So such types of the sheets are not used for the certain analysis, or it is not used for some of the applications. Only for the demonstration purpose that urethane rubbers are used, and sometimes it is also used for some of the dynamic application, but it is in less quantity. Then the fifth property is the epoxy resin. So it is also one of the important material which is used for the sheet casting. In addition to that, that epoxy resin is also used as a one binder, because whatever the composite materials are there, that is glass fiber, carbon fiber, Kevlar fiber, all these materials are bonded together by using the epoxy resin. Means that epoxy resin is having the two advantages, that is, it is used for the preparation of casting, sheet casting. In addition to that, it is also used as a one binder, or it is also used as a one adhesive material for the sticking purpose. So this is about the epoxy resin. And mostly the epoxy resin is also used for the preparation of sheet casting. And the last, that is araldite and the hardener. As we discussed that araldite and hardener, nowadays it is very easily available in the market with a reasonable cost. Therefore mostly that araldite and the hardeners are used for the preparation of a sheet casting. So these are the total 6 materials which are used for the sheet casting, but as already I have told, it is having some properties, and that properties are available in the form of some advantages are there, some disadvantages are there. As per our requirement, we have to select that particular material, and by using that particular material we have to prepare the sheet. But mostly, as already I have told, that epoxy resin and the araldite and hardener, these two materials are mostly used for the sheet casting. So this is about the different materials or the various materials used for the sheet casting. Now the next point is very important, that is calibration of photoelastic model. So the definition of calibration is very simple, but the definition of calibration is different in the subject of measurement, and here in the ESA the calibration definition is different. So in the measurement subjects, so calibration means whatever the results are obtained, that results we have to compare with the standard values. That means you have done any experimentation, and during the experimentation whatever results are obtained, if I will compare that particular all the results with the standard value, then that process is called as a calibration. But here in our subject, the calibration method is totally different. That is, what is the definition of calibration? The calibration of photoelastic model means to find or to establish the material fringe value, that is F sigma. So what is meant by the calibration? To find or to establish the material fringe value. So if you go through this particular formula, so this particular formula is obtained from the stress optic law. What is that formula? Sigma 1 minus sigma 2 is equal to N into F sigma by H. So up to the chapter number 2, what assumptions we have considered? That is, if I have to calculate this particular sigma 1 minus sigma 2, so before that calculation I have to know N, I have to know F sigma, and I have to know H. But in that, out of this particular 3 parameters, that F sigma value and H value as a given parameter, and that N parameter we can calculate by using the Tardis method or by using this particular Babinet-Saussure method, and that n we can put here, and by using this particular three parameters I can calculate the sigma 1 minus sigma 2. But now in this chapter number 3, what is our requirement? I have to calculate the f sigma value. So to calculate that particular f sigma value, what is my requirement? In the same formula, so we have to select that model whose sigma 1 minus sigma 2 is known. That means if we have to perform the calibration of any photoelastic model, whatever the model we have selected, for example, if I will selected a circular disc, so whatever the circular disc I have selected, so before calculating that particular f sigma value, whatever the disc I have selected, so for that particular disc I have to know the sigma 1 minus sigma 2. So if I will know the sigma 1 minus sigma 2 of that particular disc, if I will know the n and the thickness, then I can calculate the f sigma value, and that f sigma value of the photoelastic material should be in between 12 to 16 Newton per mm. So if it is in between 12 to 16, then and then only we can say that your photoelastic model is more sensitive. If the value of f sigma is increases more than 16, or if it is less than 12 Newton per mm, then the sensitivity of such types of the models is goes on decreasing. Therefore that f sigma value should be always in between 12 to 16 Newton per mm. So now from this particular formula, as I have understood that if sigma 1 minus sigma 2 is given to me, if n is given to me, and h is given to me, so from this particular three parameters I can calculate the f sigma value. So for that purpose, during the calibration process I have to select that model whose sigma 1 minus sigma 2 is known. Therefore during the calibration we have to select that model whose principal difference is known, fringe order n, and the thickness of model is given. So this is the requirement of the model during the calibration purpose. But how the calibration is done? So whatever the sheet is prepared by using the casting process, so for that particular whole sheet or that particular big sheet, it is not possible to calculate the f sigma value, because that big sheet is not possible to attach in the polariscopic device. So for that purpose, what we have to do, from that particular sheet we have to cut the different types of models, and that models are inspected, means whatever the f sigma value we are going to calculate, we have to calculate that f sigma value for all that particular models, and the value of f sigma for that particular model will be considered as a value of f sigma for the whole photoelastic sheet. Means for example, if I have taken the circular disc, so whatever the f sigma value is calculated for the circular disc, same f sigma value of the circular disc will be considered as a f sigma value of the whole sheet. Therefore usually for the calibration purpose, the tensile specimen, circular disc, or the beam model are selected for the calibration purpose, because in all the three models we are applying the different types of loads. That means in the tensile specimen we are applying the tensile load, we have to go for the calibration. In circular disc we have to apply the compressive load, again we have to go for the calibration. In beam model we have to apply the bending load, again we have to go for the calibration. Therefore these three models are selected for the calibration purpose. Now we'll discuss about the first method, that is calibration of photoelastic model using tensile specimen. So now in the first calibration procedures, we have selected the tensile specimen for the calibration purpose. So what we have done exactly here, so as the calculation of f sigma value is not possible for the whole photoelastic sheet, so for that purpose what I have done, from that particular sheet I have cut one tensile specimen, and that tensile specimen is inspected in the polariscope, and by using that particular polariscope I have calculated the f sigma value for the tensile specimen, and whatever the f sigma value is calculated for the tensile specimen, same f sigma value will be considered as a f sigma value of the whole photoelastic sheet from which I have cut that particular tensile specimen. So in this particular first method, as I have selected tensile specimen for the calibration purpose, so in this particular first method we are going to derive a one small derivation. In that derivations we are going to derive one formula for the F sigma value, that is if the tensile specimen is selected for the calibration purpose. How the F sigma value is calculated by using the tensile specimen means we are going to derive one formula of F sigma, and by using that particular F sigma value I can calculate, or by using that particular formula I can directly calculate F sigma value for the tensile specimen. And same procedure we are going to follow for the circular disc and the beam model, and we are going to derive the three different formulas in that particular calibration of photoelastic model. Now we'll first see that is tensile specimen. So for that particular concept I have selected a tensile specimen. If you go through the figure, so the first figure represents the actual tensile model which we have cut from the whole photoelastic sheet. Their cross sectional area is also considered, that is W represents the width of that particular central portion, H represents the height or thickness of that particular central portion. Why the central portion is considered? Because when the load is applied on tensile specimen, so whatever the nick formation will taking place, whatever the breaking of the tensile specimen is taking place, it is taking place at this particular central portion. Therefore this cross section area is considered for the calibration purpose. The second figure is also represent the same, that is this is the three-dimensional figure, this is the two-dimensional figure, that is as per the requirement of the tensile specimen, or as per the name suggests, that is the tensile specimen is always subjected to the tensile loading. So if you go through the second figure, that P represents the tensile load applied on the tensile specimen, that W represents the width of tensile specimen, and height represents the thickness or height of that particular central portion. Now how we have to do the calibration, or how the formula should be derived? So for that purpose we have to consider some of the conditions, that is we have to consider a specimen having width W and thickness H, which is shown in the figure, and whatever the load is applied on the tensile specimen, that load is called as a tensile load. So whatever the P amount of load is applied on tensile specimen, due to that P amount of load some amount of stress is also developed, and the stress developed due to the tensile load is called as a tensile stress. And whatever the stress developed in the specimen due to the load P, that stress is indicated by sigma 1, and that sigma 1 is calculated by using the simple formula, that is stress is equal to force upon area. So that sigma 1 represents the tensile stress developed in the tensile specimen after the application of load P, and by using the simple formula, stress is equal to P upon A, therefore sigma 1 is equal to P upon A is equal to P upon W into H. So that cross sectional area is considered as a central portion of the tensile specimen having width W and the thickness H, that is sigma 1 is equal to P upon W into H. This is the equation number 1, which represents the tensile stress induced in tensile specimen after the application of load P. But as we know that whatever the secondary principal stress is there, the secondary principal stress means that sigma 1 is represents the primary principal stress, and the sigma 2 represents the secondary principal stress. So whatever the secondary principal stress is there, that secondary principal stress is always equal to 0 in the photoelastic material. So for that purpose we have to take one formula, that is stress optic law is equal to sigma 1 minus sigma 2 is equal to N into F sigma by H. So this is one standard formula which is available in the experimental stress analysis. In this particular formula we have to consider one assumption, that is whatever the secondary principal stress is developed in the photoelastic model, that secondary principal stress is always equal to 0. That means if I will put sigma 2 is equal to 0 in this equation 2, that is once again I will get one formula, that is sigma 1 is equal to N into F sigma by H, that is equation number 3. So sigma 1, that is equation number 1, represents tensile stress induced in the tensile model or the tensile specimen sigma 1, and this sigma 1 represents the stress obtained from the stress optic law. So if I will compare the equation number 1 and equation number 3, so their left hand sides are equal, that is sigma 1 sigma 1. So due to this condition their right hand sides are also equal, therefore the equation becomes F sigma is equal to So your equation sigma 1 is equal to n into f sigma by h. So if I will compare the equation number 1 and equation number 3, the right hand sides are equal, and as I have to calculate the value of f sigma, so that equation is directly written in the form of f sigma, that is f sigma is equal to p into h divided by w into h into n. So h from the numerator, h from the denominator, it will get cancelled, and finally I will get one equation, that is f sigma is equal to 1 upon w into p by n, and this is the standard formula of f sigma which we have derived for the tensile specimen. That means if a tensile specimen is selected for the calibration purpose, so for that particular tensile specimen, by using this particular f sigma formula, directly I can calculate the f sigma value for the tensile specimen. But what is our requirement? Whatever the w is given, that is w is the standard parameter, that is the width of the tensile specimen at the center portion, but whatever the p by n is there, that p by n is calculated from the graph. So in this particular above equation, to calculate the value of p by n, what we have to do, we have to draw the graph of p versus n. That means as the load is increases, the fringes are also increases, and this particular graph is perfectly linear, that is p is directly proportional to n. So according to that, how the p by n is calculated from this particular graph, I have to calculate the slope of p versus n, and by using that particular slope value, I have to put that particular p by n in this above equation, and from that equation I can directly calculate the f sigma value for the tensile specimen. So this is the actual derivations we have derived for the tensile specimen, in which what we have considered, we have considered a one tensile specimen, it is subjected to the loading condition, that is tensile loading condition. So due to that load p, we have calculated sigma 1, that is tensile stress, which is our equation number 1. Then in the stress optic law, we have considered a one assumption, that is sigma 2 is equal to 0. Again from this equation, again you will get one sigma 1. So by comparing equation number 1 and equation number 3, you will get the final formula of f sigma, and that f sigma value represents the calibration of photoelastic model using tensile specimen. So this is the first method of the calibration of photoelastic model. Now the second method, is the circular disc. So in the circular disc, what we have to do, once again, whatever the sheet we have prepared from the casting process, from that particular sheet, once again we have to cut one circular disc, and we have to calculate that f sigma value for the circular disc, and once again whatever the f sigma value is calculated for the circular disc, same f sigma value will be considered as a f sigma value for that particular sheet. But now here I have to do the calibration by using the circular disc. So if you go through the figure, so the figure consists of a one circular disc, and the circular disc is always in the diametrical compression, means the circular disc is always subjected to the compressive load. So according to the loading condition, here the p is there, here the p is there, both are equal in magnitude, opposite in nature. That means according to this particular direction, the disc is under the diametrical compression. So for that particular disc, the capital D represents the diameter of disc, this H represents the thickness of model, and this is the one standard formula which is used for the calibration purpose, that is f sigma is equal to 8 p d raised to 4 minus 4 d square x square divided by pi dn in bracket d square plus 4x square bracket square. So this is one standard formula which is used for the calibration of photoelastic model using the circular disc. But here in the circular disc, what we have to do, I have to calculate the f sigma value at the different locations, means if I have to calculate the f sigma value at the center point, formula is different. If I have to calculate the f sigma value at some distance from the center point, again the formula is different. That means here to derive this particular formulas, here in this particular equations I have to apply the sum of the boundary conditions, and in this particular equation, what that x represents, here x parameter is there, here x parameter is there, that x represents the distance of point from the origin. That means here origin is present, here one more point is there, and distance between point O and this particular new point is represented by x, and that x distance we have to put in this particular equation for the further calculation. So now initially my requirement is that I have to calculate the f sigma value at the center point, that is at the point O. So at this particular point O I have to apply the boundary condition. So what boundary conditions I have to apply? That is, if I have to calculate the f sigma value at the center point, what is the value of x? So value of x is equal to 0 at the center point, that is I have to put x is equal to 0 in this particular equation, and if I will put that particular value, that is if I will put that x is equal to 0 in this particular above equation, I will get the new formula, that is f sigma is equal to 8p upon pi dl. So this is the standard formula available to calculate the f sigma value at the center of disk because x is equal to 0. Now if I have to calculate the f sigma value at some distance from the center point, that is x is equal to x1, that means from the center point I have selected one point, that is from the center point your new point is at the 9 centimeter, that means your x distance becomes the 9 centimeter. Then means once again I have to put the second boundary condition, that is x is equal to x1 in the above equation, and the same equation will be written in the form of x sigma is equal to 8pd raised to 4 minus 4d square x1 square, because x is replaced by x1, and whatever your x1 distance is there, maybe 8 centimeter, 9 centimeter, 10 centimeter, that distance we have to put here, and we have to calculate the f sigma value. And same procedure we have to follow, that is one point is selected at a distance of 7 centimeter, another point is selected for 8 centimeter, then 12 centimeter, like that x parameter we have to vary in this particular equations, and we have to calculate the f sigma value for the different points. But what is the requirement? Whatever the f sigma value is calculated at the center point, whatever the f sigma value is calculated at some distances from the center point, all the f sigma values should be near to each other. Means for the center point you will get the value 30 Newton per mm. Then from center whatever the points we have considered, at one point you will get the value 12.35. For the next point I will get the value 40 Newton per mm. So all the values which are near to each other, means from that particular process we have to go for one assumption, that is whatever the f sigma value is calculated at the different location of the circular disc, all the f sigma values should be same. Why? Because your photoelastic sheet is having one property, that is isotropic and the homogeneous. Isotropic means the material should have same properties in all direction, and as this material is prepared by using the number of particles, so each and every particle is having the same properties. If all the properties are same, then whatever the f sigma value we are going to calculate at center point or at some distances from the center point, all the f sigma value should be same, and that f sigma values I have to calculate in the circular disc. So this is about the calibration by using the circular disc, in which only we have to apply the boundary condition, that is x is equal to 0, then x is equal to x1, x is equal to x2, x is equal to x3, like that we have to apply, or like that we have to vary only x distance, and according to that x distance I have to calculate the number of f sigma values. If I have calculated the number of f sigma values, then finally I have to take the average of all the f sigma value, and the final f sigma value will be considered as a f sigma value for the circular disc as well as f sigma value of that particular sheet from which the disc we have cut. So this is about the calibration of photoelastic model using the circular disc. And the last method, that is calibration of photoelastic model using the beam model. That means here again the loading condition is different. So if you go through the figure, it consists of a one beam. So whatever the beam here we have prepared, that beam is also prepared by using the same photoelastic sheet. That means whatever the sheet we have prepared by using the casting process, from that particular sheet I have to cut one small a rectangular plate, and that rectangular plate will be considered as a beam model. So according to the requirement, as we have considered a beam model, so according to the requirement of beam, we have to apply some boundary conditions. That is, one beam is prepared by using the photoelastic sheet, which is supported by the hinge support and the roller support. The p amount of load is applied on that particular beam model. Whatever the cross sections we have considered, that is w represents the depth of model and h represents the thickness of model. Means w represents the depth of beam and h represents the thickness of beam. Now here, if the beam is subjected to the loading condition, there is no any tensile stress, there is no any compressive stress, because the tensile stress is developed in tensile specimen, compressive stress is developed in the circular disc. But in case of a beam model, as the beam is subjected to the loading, the bending of the beam is taking place. Means after the application of load on any type of beam, that beam is subjected to the bending moment, and that bending moment we have to use to derive the formula of F sigma for the beam model. So for that purpose, what we have considered? We have considered a one beam model which is supported at the two ends. The P amount of load is applied at a distance A from both the sides, and due to the application of load P, the beam is subjected to the pure bending. Means the beam is under the bending moment, and that value of bending moment is used to derive the formula of F sigma value for the beam model. So if you go through the derivation, so initially your equation number 1 represents the m is equal to p into a. So what is mean by m is equal to p into a? As we know that the bending moment is equal to force into perpendicular distance. So here the load is applied p, it is applied at a distance a from this particular side, that is the distance between this point and this point is a. If I will take the moment about this particular point, that is m is equal to force into perpendicular distance, that is m is equal to p into a, and that bending moment I have calculated by using the figure, that is m is equal to p into a. And as we know that due to the bending moment, the beam is also subjected to the some stress, but it is not subjected to the tensile stress, it is not subjected to the bending stress. So due to the bending moment of the beam, whatever the stress is induced, that stress is called as a bending stress, and that bending stress I have to calculate by using one formula, and that formula is called as a bending stress formula. So equation 1 represents the m is equal to p into a, that is bending moment of beam. Now the equation 2 represents m upon I is equal to sigma 1 upon y. So this equation 2 represents the bending stress formula. So in that equation, m is equal to bending moment, I is equal to moment of inertia of that particular beam, sigma 1 represents the bending stress induced in beam due to this particular bending moment, and y represents the centroidal distance. Okay, so the I is calculated by using the cross sectional area, as the rectangular cross section is there, that is b into d cube divided by 12. But here, what is the cross sections we have considered? That is w is the depth of section, that is it will be replaced in the form of d. H represents the thickness of that particular beam model, which will be replaced in the form of b. Therefore your equation becomes I is equal to bd cube divided by 12 is equal to h into w cube divided by 12, because h is in the form of b and d is in the form of w. Therefore I is equal to bd cube divided by 12 is equal to h into w cube divided by 12. Then y represents the centroidal distance. So whatever the CG of that particular beam is there, that CG is concentrating at this particular point, and where that CG is there, center of this particular cross section. And what is the center of this particular cross section? That is y is equal to w divided by 2, and that y is represented, or it is calculated from the figure, that is y is equal to w by 2. So what we have to do, we have to put this particular I value and y value in the above equation, that is in the bending stress formula, and your equation becomes, what is your equation? That is m is equal to p into a, that is m is equal to p into a, we have taken from the equation number 1. Then I is equal to h into w cube divided by 12, we have put this particular value in this particular equation. Then sigma 1 I have to keep as it is because this is our requirement, that is to calculate the bending stress. Then y is equal to w by 2, that value we have to put in this particular equation, and by rearranging the terms, that is 12 I will take to the numerator, 2 I will take the numerator, and the final equation becomes 12 into p into a divided by h into w cube is equal to 2 I have taken at the top side, therefore equation becomes 2 into sigma 1 divided by w. But my requirement is that I have to calculate the bending stress induced in that particular beam, and by rearranging the terms, by cancelling the sum of the terms from the numerator and denominator, I have derived the basic formula for the sigma 1, that is sigma 1 is equal to 6 into p into a divided by h into w square, that is equation number 3, and this equation number 3 represents the bending stress induced in the beam model. Same sigma 1 we have calculated in the tensile specimen also, but that sigma 1 represents the tensile stress induced in tensile specimen, and this sigma 1, that is this equation number 3, represents the bending stress induced in beam model when beam is subjected to the bending moment. So this is the bending stress we have calculated by using the bending stress formula and by using the bending moment. Now second equation, again we are having the second equation, that is stress optic law, which is used in the experimental stress analysis, that is sigma 1 minus sigma 2 is equal to n into f sigma by h. So as we know that whatever the secondary principal stress is there, that secondary principal stress is always equal to 0. So if I will put the sigma 2 is equal to 0 once again I will get the same equation in the form of sigma 1, that is sigma 1 is equal to n into f sigma by h. Again the left hand sides are becomes equal, therefore the right hand sides are becomes equal. So your equation becomes from this equation, from this sigma 1 equation and from this particular stress optic law, I will get the next equation, that is 6 into p into a divided by h into w square from this equation number 3, and n into f sigma by h. That means after comparing this sigma 1 equation and this stress optic law, as this particular left hand side becomes equal when sigma 2 is equal to 0, at the same time this two right hand sides are also becomes equal to 0. So I will get this particular steps, and as my requirement is that I have to calculate the f sigma value, so same this equation I have written in the form of f sigma by rearranging the terms, that is f sigma is equal to 6 into p into a into h divided by h into w square into n. So here h from the numerator, h from the denominator will get cancelled, and I will get the f sigma 6 into p into a divided by w square by n, and once again by rearranging the terms, the final equation will be written 6 into a divided by w square into p by n. That means that a represents the distance between load applied on the beam and the free end, w represents the depth of that particular beam, and that p by n represents the force applied on that particular beam, and the fringe order passes through the point of interest. And once again the value of p by n is calculated from the graph. That means I have to draw the graph of p versus n, and by taking the slope in between 2 points, and that slope value I can directly put in this particular p by n equation, and from this particular f sigma value directly I can calculate the material fringe value by using the beam model. So this is the derivation of the beam model, that is calculation of f sigma value for the beam model. So in this particular calibration of photoelastic model, basically we have derived the three formulas for the f sigma value. That is first formula for the tensile specimen, that is f sigma is equal to 1 upon w into p by n. Second formula, f sigma is equal to 8p upon pi dn for the circular disc, and for the last model, that is beam model, f sigma is equal to 6 into a divided by w square into p by n. So in all the three equations you will get this particular parameter p by n, and that p by n is calculated by plotting the graph of p versus n, which are linear to each other, and by taking the slope in between 2 points, and that slope value will be directly kept as a p by n in the f sigma equation. So if we compare all the f sigma values with each other, all the three formulas are different because models are different. Means in tensile we have applied the tensile load, so formula is different. In circular disc we have applied the compressive load, again the formula is different. And in the last beam model we have applied the load due to which the bending moment of the beam is taking place and the bending stress is developed, and according to that again the formula is different. Like that the calibration is done for the photoelastic model. So these are the three methods of the calibration purpose which are used in the concept of photoelasticity for the calibration purpose. So this is about the chapter number 3, that is photoelastic material. So once again I will take the overview of this particular chapter. So in the starting, what we have discussed about the basic 11 properties of the photoelastic material or the photoelastic sheet. Then we have discussed about the casting technique, how the photoelastic sheet should be prepared in the casting technique, what care should be taken while the preparation of mold, while the preparation of liquid, that we have discussed in the casting technique. Then we have discussed about the different materials used for the sheet casting. So total 6 materials we have discussed. Each and every material is having some of the advantages and disadvantages. That advantages and disadvantages also we have discussed in this particular chapter. Then we have discussed about the calibration of photoelastic model, why calibration we have to do, that is and how it is do. So by using this particular formula I have explained how the calibration is done and how to calculate that particular f sigma value. And then we have discussed about the 3 methods, that is tensile specimen, in that we have derived one f sigma formula. Then in the circular disc again we have derived one more f sigma formula, and in the last method, that is beam model, in that also we have derived the separate f sigma formula for the calibration purpose. So this is about the chapter number 3, that is photoelastic materials. Thank you.